I've got one on question 3 of homework 7.
Question 3 of homework 7. I actually brought my sheet.
Okay, is that the same one as this one?
Maybe. Yeah, well, it should be. Yeah.
Let's see, I had 2 questions. First question was, at the end of the day, the I1 ends up orders of magnitudes larger than I0. Is that at least how I calculated it?
Inside the fabric burrow.
Inside the fabric burrow,
Yeah.
right?
Yeah.
And then my other question was, it turns out that you have to assume that the fabric burrow is, like the delta is a multiple of 2 pi, and it turns out that that's also for maximum transmission. Are those 2 effects related, the max transmission and the fact that it constructively interferes?
Yeah.
Okay.
Yeah. Yeah, so in order to have energy build up in the cavity, you have to have constructive interference in the cavity.
Yeah.
So therefore, that constraint on the length,
Okay.
which is also a transmission mode of the cavity. Yeah, oh, and I steered you wrong on 2 when you asked me the other day.
Oh.
Okay.
Okay.
We
That's
just
what we
moved
thought.
on, and we were like.
Yeah. No, so the phase shift.
Here it comes.
Yeah. Well, I didn't remember what my question was asking. That's the problem. So you have R121. It's a complex number, so you can always write it as a magnitude and a phase. And so it's asking for that phase.
Oh. Okay.
That was my first
Yeah, that was
guess.
his first.
Okay.
Yeah.
Okay.
Yeah, so that's what you're looking for. So it's just output.
Okay. All right, thanks.
Okay. All right, any other questions?
When do you have planning on having this last homework due?
Last day of class.
Okay.
Yeah. Mhm. Yeah. Yeah, let's do that.
Only a week left.
Yeah.
So are you going to give us the solutions when you turn in the homework? Or?
I could, yeah.
Because I figured that when we turn it in, we won't be able to get the solutions for studying in lessons.
Yeah, it'd probably be good to remind me to do that, but I can definitely do that.
Okay.
That's fine.
What's the finals layout going to be?
Just some problems.
Yep.
Yeah, nothing crazy. So, but the final will be open book. Conveniently, we don't really have much of a book.
I mean, the notes are basically.
So
textbook
open notes, open homework solutions. The only thing that's not open is neighbor. Not open neighbor. It should be an individual effort.
Are you considered a neighbor?
Huh?
Are you considered a neighbor?
Yeah, any other human being is a neighbor. Yeah, you can ask your dog, I don't care.
Was this timed or taken?
Take them. Yeah. Yeah. Yeah, I don't want anyone to be penalized if they are slow at it. Okay, and then we can talk about next week on Thursday when to make it due. So, yeah.
I'm leaving Tuesday, so
Yeah, well, my daughter comes home on the 19th from Finland from a mission, so I'd really like to have it all done before then.
done by graded.
Yeah,
Fair enough.
yeah. So, but if you think that's not going to give me enough time, we can talk about it. So we decide. Okay. Any other questions? Just don't tell Jace what we talked about, okay? All right. Okay.
No.
So, what are the? So, if I ask you, say on the final, to design a single layer AR coating, what would you do?
Single layer of air coating.
Yeah, for some wavelength at normal instance.
First, you'd want to know what materials you have available.
Mm-hmm. Yep. So let's say you know what materials you have available. What do you do?
calculate your D, right?
Yeah, and D will be what?
It'll be your lambda naught over 4, 1, 2, quarter wavelength and other.
So quarter wavelength in the material. In the material you have,
Yeah, when you
not the ideal one you wish you had. Okay, and what else?
The refractive index of that material is the square root of the product of the other two. It's between
The ideal,
the ideal.
for the ideal, yes.
And you want to pick what you can get
Oh.
closest to.
So if I ask you to design one, then basically you're going to tell me what the thickness of the film is and what the refractive index is of what you want to have. And then if you don't have it, then you probably need to calculate, well, what's the residual reflectance you're going to get, which is not a big deal to calculate. Okay. Okay, so thickness, quarter wave, refractive index. All right, so what we want to do now is look at a two-layer AR coating. And I want to go through this just to give you a sense of a couple of things, but one of them is going to be how tedious this can be. And that motivates some other stuff that we'll talk about. Okay, so let's say that we have here a substrate of fused silica. So refractive index 1.46. And we want to figure out how to make an air coating that will be really good at normal instance. Although this could be at any angle of instance. And so rather than just one layer of material, let's put on two layers. So let's say we put some material here with some thickness, call it D3, and another layer here with some thickness, call it D2. And let's say that, let's not worry about what the material is here, let's just leave it generic. So refractive index N4, refractive index N3, refractive index N2, ambient material refractive index N1. Okay, we look at this system, and if we're in N2, looking this way, this is just a thin film on a substrate. So the reflection coefficient here is R2, 3, 4. Where R2, 3, 4 is going to be R2, 3 plus R3, 4 e to the j minus j delta 3, let's call it, over 1 plus R2, 3, R3, 4 e to the minus j delta 3. And delta 3 is going to be 4 pi over lambda naught N3 D3 cosine theta 3. Right? It's just what we did last time for a thin film on a substrate, but now just having the appropriate subscripts on the quantities. Okay, so we're all right with that? Okay. So if I'm here and I just look at this first interface, that's going to be a reflection coefficient of R12, just for the first interface. This one takes into account, this whole system. And now, if I have R12 here, N2, and R234 for everything to the right, then basically this looks like a thin film on a weird substrate. So we can immediately write down what the reflection coefficient is for the entire system, R1234. It will be R12, reflection coefficient of the first interface, plus R234, reflection coefficient of the second interface, times e to the minus j delta 2 over 1 plus R12, R234, e to the minus j delta 2. So that wasn't very hard to write down what the reflection coefficient is or a two-layer system. It's just, take this as a three-layer system, and then this becomes a three-layer system with just a more complicated reflection coefficient here. And we could do this ad nauseum for any number of layers, but let's just leave it at 2. So delta 2 here is 4 pi over lambda naught n2 d2 cosine theta 2. Okay, so now we have expressions.
Why do we pick delta 2, just because it's the furthest to the left of our combined?
Because it has to do with the phase shift going on in this layer, which we're calling, we're subscripting with a 2. And
So it
likewise,
picks up in that layer, right?
yep, it's the phase shift
Or
for
rather uses,
the
I
front
guess.
surface versus the back surface reflection just in this layer.
I guess I was just looking at why it wouldn't be like D2 plus D3, for example.
Well, D3 pertains to this one.
Right, but aren't we like grouping them all as one?
Well, we already know the reflection coefficient from this interface on.
Yeah, so the R2,
Yeah,
3, 4 already
R2, 3, 4.
takes that phase shift of everything to the right.
Yep.
And so you're just basically adding that.
It's already accounted for.
Exactly. Yep. Yep, good question. Okay, so if we want to make an anti-reflection coating out of this system, then we must have that R1, 2, 3, 4 is equal to 0. Which means the numerator has to be equal to 0. So R12 plus R234 e to the minus j delta 2 has to be equal to 0. Now, if n1, n2, n3, and n4 are given, then there's only two things we can play with, d2 and d3. So given a particular instance angle, just d2 and d3, those are the two knobs we have to turn. And the strategy is as follows. What we want to do is basically choose, actually let's do this, choose D3 such that the magnitude of R234 is equal to the magnitude of R12. So basically, by changing D3, we can continuously change the magnitude of R234 between two limits. So we want to choose the value of D3 that makes the magnitude of R234 the same as the magnitude of R12. Then, if these two things have the same magnitude, we want to choose D2 so that the R234 term has the opposite sign to the R12 term. So R234 will have the same magnitude as R12 from number 1, and then it will have some phase, whatever it is. So we want to choose D2 so that this phase term cancels out the phase term of this and flips the sign relative to that. And then this will be equal to 0. So that's our strategy. Okay, so let's do an example. Let's say that we have the following. Let's say that this is fused silica, so N4 is 1.46, and this is air, so N1 is 1.0. And then let's say that we're using mag fluoride, and so we'll do mag fluoride for the top coating, so N2 is 1.37, And let's say we use mag oxide for the first coating. And so that has refractive index of 3 of 1.76. So that's the system we want to use. And now we just need to figure out, first of all, what is D3, and then what is D2. So to figure out D3, then what we need to do is note that, and we want to do this for normal instance. So first we note that R12, if we calculate that, so 1 minus 1.37 over 1 plus 1.37, then that gives us a value of minus 0.156. So we want the magnitude of R234 to be 0.156. So the first thing we need to do is figure out, well, is it possible? And we can see if it's possible by looking at the extreme cases. And the extreme cases are, first of all, D3 equals to 0. Right? We don't have that material there. If D3 is equal to 0, then R234 is going to be equal to R24. And we can easily calculate that. That's minus 0.032. Okay, the other extreme case is when this is a quarter wave thick. And so if we go back to R234, put in D3, yeah, put in D3 of a quarter wave and work that out, what we find is that R234 is equal to minus 0.215. And we look at that and we say, oh, okay, well, 0.156 is between 0.032 and 0.215, so yeah, it's possible. We can do this. Okay, good. So then we perform a calculation.
Oh, sorry.
Yeah.
Is that assuming that quarter wave would give you the maximum?
It does. Yeah, it does. So those are the two extreme cases. As you increase D3, then you basically come back towards D3. I mean, come back towards D3 equals 0 case.
Because it's periodic.
It's periodic.
What's due to that?
Yeah. Mm-hmm. Yeah. Okay. So we can do the calculation, and basically, and it's a root finding calculation, so you have to do it numerically. But we calculate it, and we find that D3 is equal to 35.6 nanometers. And in that case, R234 is equal to 0.156 e to the minus j, 2.51 radians. So for this D3, that's what we've got. Okay, so now what we need to do is calculate what D2 we need in order to cancel out this 2.51, minus 2.51 radians, and that's all we have to do because this is already a minus sign. So we perform that calculation, and what we end up with is that D2 is equal to 109.6 nanometers. And then we're done. That's it. So we have a 2-layer AR coat. And it should work really well. We'll look at a plot in just a minute, after we do another case.
So, in order to find your D's, did you just have to find out the, what is that squiggly music sign?
Delta?
Delta. You have to pick the delta D2, right? Or
Uh,
D3, whichever one, you just have to.
well, so basically you have this equation and you set it equal to a magnitude, or did I write it down?
Up there, number one?
Yeah, you basically say, oh, I want this to be,
You have it right here under the drawing, the negative 0.56.
yeah, so I want this to be 0.156 e to the j something is equal to this stuff, which is a function of d3. And I don't care what that is. So basically I run through a bunch of d3s until I get that magnitude. And then that's what it ends up being. So you do it numerically, not analytically. And then D2 is simple. You're just looking for this equal to 2.51 radians. Okay, so it's not too bad. There's one numerical solution step. All right, so let's now look at another example. Let's say that we have the same fused silica over here. And let's say that we flip the order of the film, so this is mag oxide and this is mag fluoride. Then the question is, can we do a two-layer air coating? So we calculate R12 and we find that it's minus 0.275. And then we look at R234 for the case of D3 equal to 0. So we have R24, and that ends up being 0.093. And then we look at D3 equal to a quarter wave. And what we find is that the magnitude goes to minus 0.156. And we look at that and we say, oh, well, 0.275 is not in that range, therefore we cannot make a two-layer coating.
Is that R24?
Yeah. Yeah, which would be, I might have these split. But at any rate, the only point I want to make is that order can definitely matter. Where it'll work one way, but you flip the order and it doesn't work. Yeah.
So with microwave engineering, they use this technique, and the higher index, or I should say the higher impedance, is always they're kind of like stepped. So, but it allows for a wider bandwidth to kind of get through. Is a similar case kind of with this? Like, do they go up to 2, 3, 4 layers just to allow even better anti-reflection?
All the same things apply. Yep. Yep. Exactly right.
So should they typically be in ascending order then? Or is that not the thing?
Not necessarily. Yeah, I mean, I haven't done enough fiddling with it to have a rule of thumb off the top of my head. Yeah. Okay, so now what we want to do is take a look at what happens when you, I mean, these are designs and calculations for normal instance for single wavelength. So we want to know what happens when we change that. If you want to flip on that guy. Okay, let's do this. Yeah, there we go. Okay, so first thing, let's look at reflectance as a function of instance angle. Yeah, notice the date over there? It's a long time ago. Actually, I think I did these in 1995. And then I did a little update in 2003. So, they're timeless. So if we look at the reflectance, so magnitude reflection coefficient squared, so it's the power quantity, as a function of instance angle, and we've designed for normal instance. And this is fused silica and single layer coating of mag chloride. It's a quarter wavelength thick. And then notice you get down to, a little less than 2% on the reflectance. Not that great. And then as you go off normal instance, it just, increases. And when you're over at a shallow grazing angle, then it just looks like a mirror, as usual. Okay, if we go to the two-layer design that we just did with mag fluoride and mag oxide, at normal instance, we can't believe this number because of numerical error. So basically, in the ideal case, it's really, really small. Many orders of magnitude better than a single layer coating. And then as we go off normal instance, then of course it breaks down. And we get more and more reflectance, but notice for all angles it's better than a single layer coating. So this is for TE polarization. Okay.
So is this caused because we couldn't find the ideal material we wanted?
Yes, that's exactly right. So we can't find the ideal material, so we use two materials, and then we can do awesome at the design point. So, and notice this is for 500 nanometer wavelength. Okay, so then we go to TM, and similar sort of thing, except for the single layer case, as we go off normal instance, we actually get better. Because we're going to go hit the Brewster angle, and then after the Brewster angle it comes up as usual. For the two-layer case, then at normal instance we do awesome. It just comes back down to manufacturing variations in terms of what you actually get. And then you still do better for a two-layer case all the way out to about 40 degrees plus or minus. So two-layer is really, really good in comparison to one layer with a non-ideal material. Okay, so that's for a very specific wavelength, the design wavelength. What happens is we vary wavelength. So this is at normal instance, the one layer and the two layer coating, and 500 nanometers is the design wavelength. And you notice for the one layer coating, it just doesn't really change very much. So it's just whatever it is, plus a little bit as you go off the design wavelength. For the two-layer coating, when you do great near the design wavelength, and you still beat the single-layer coating out to 425-ish nanometers and 640-ish nanometers. So the two-layer coating still does really good over, or better than the single-layer coating over a wide wavelength range, almost the entire visible range.
So would this be like what we saw on people's glasses where it spikes up and that's quickly the low
Yep.
for groups?
Exactly. This is exactly what we saw. So if we have a good air coating, that's for a two-layer case. So if we have a good two-layer coating, then it's going to look kind of violet here. And then once we get past this, our eyes are starting to cut out in terms of its spectral responsivity. So, yeah, so a good coating will look bush. Okay, so now you've got a little bit of a feel for what happens when you go off the design wavelength here, or off the design instance angle. So
So 2-layer coatings are great.
So if we went to like a 3-layer coating, would these effects get worse, where it would like be really fantastic, but then it would like pull up sooner on the spectrum?
It depends. Yeah, it depends on how you do the design. And so, right now, the natural thing to do would be to dive into multi-layer thin film design, which I would love to be able to do, but next week's the last week of class. So we're not going to do that in all its glory. Instead, we're going to do a sort of a partial approach to understanding what happens with multi-layer designs. So, what we're going to do is pull out this old paper. And this paper is by some folks at UC Santa Barbara. And basically, it's going to use a trick to be able to analytically analyze multi-layer stacks. And the trick goes back to a hyperbolic tangent identity. So if you take a look at this diagram here, there's basically a Fabry-Perot with reflectance at each surface, which in general can be different, and the phase difference between the front and back surface reflection. And so, here's the reflection coefficient for the system, which looks very familiar. It just has different notation than what we used in class. And then over here, this hyperbolic tangent identity gets used because if you look at that and compare it to this, it looks similar, right? So it turns out that we can use that if these e to the minus j phis go away. And so those e to the minus j phis go away for certain values of phi. If phi is pi, then this is just 1. I mean, rather minus 1 in both cases. Or if phi is 2 pi, then this is 1. So in other words, for very specific layer thicknesses, the e to j phis become real, plus or minus 1, and we can use this substitution technique. So a e to the minus j, well, a phi of pi is a quarter wave thickness. A phi of 2 pi is a half wavelength thickness. So basically the method developed in this paper applies to quarter wave stacks where each layer thickness is either a quarter wavelength or a half wavelength. And if you restrict yourself to that case, then you can do everything analytically using this hyperbolic tangent substitution method. And that's what the paper is about. So, if we go a little bit further into the paper, here's a stack where the substrate has a high refractive index, the instant material has a low refractive index, and then here we're just alternating high-low, 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 and requiring that these be either a quarter wave or a half wave. And if we do that, then we can end up using this substitution technique, and the stack ends up becoming the sum of these arc hyperbolic tangents, and then we can calculate the total reflectance for an n-layer stack by a very simple analytical equation where these things are pretty easy to calculate through just inverse hyperbolic tangents. So that allows us then to figure out what the reflectance is for arbitrary stacks, arbitrary numbers of layers. Okay, yeah.
How do you take into account the wavelength in these equations?
Well, that comes from the fact that each each layer is a quarter wave or a half wave thick. So the designs are always for a specific wavelength.
Okay.
Okay, so then you can do things like, well, first of all, if we look at this, so this might be, say, gallium arsenide, and this might be indium gallium arsenide. And then we have these alternating layers of gallium arsenide and indium gallium arsenide. And basically what you end up showing is that this stack, you can make it look like a really good mirror. So it's a Bragg mirror or a dielectric mirror. Two names for the same thing. If you do this, where you have basically a Bragg mirror here, another Bragg mirror here, and here you've got a lambda over 2 layer. Remember, a lambda over 2 layer is a latent layer. Yeah, it's kind of like it's not there. So it turns out this, then, is a mirror. It's in space, a mirror. Fabry-Perot. So that's a Fabry-Perot with thin film stacks. And now if I took this and I made it a gain medium, got a laser. So this is a vertical cavity surface emitting laser structure, which you can buy those off the shelf. In fact, vertical cavity surface emitting lasers really lend themselves to laser arrays in a very tiny area on the chip. And so, which has a lot of really interesting uses. Okay, so you're able to do Bragg mirrors, Fabry-Perots, surface emitting lasers. Here we have just a single layer coating on a substrate. So now we can get to anti-reflection coatings. And let's see. Yeah, so yeah, you can read all this stuff. Okay, so then doing the anti-reflection coating, we end up with, oh gee, the coating refractive index should be the square root of the product of the two other refractive indices. Okay, so here's the deal. Rather than us take class time to go through this method or to do the numerical methods that are more general, what I'm going to do is give you this paper, it's on the Lean Suite, and tell you you are responsible up to there for the material in the paper. So read it, and then 2 of the homework problems on homework 7 are using this material. And then I'll give you a final exam problem on this material. So you'll have to use it on the final exam. How's that sound? Yeah, yay. Right. Okay. So you can make a Fabry-Perot. I mean, if I were to give you some Fabry-Perot specs, finesse, reflectant, or probably finesse and 1 or 2 other parameters, then, and I gave you some materials, then you could actually use this information from this paper and design a Fabry-Perot using stacks of these materials to hit the specs for that Fabry-Perot. Yeah.
I'm vaguely remembering in some other optics class, we touched on Bragg gratings briefly. That they had like maximum reflection and used those coatings around fiber.
Oh, okay. Well, yeah. So that's Dr. Hawkins' work with aero waveguides.
I don't remember Dr. Hawkins.
Yeah. Well, I mean, that's what he does. Is he makes waveguides using these Bragg mirror structures as well. Let's take a step back. For a typical waveguide, you have some material with refractive index M2 embedded in material refractive index M1, and you propagate inside the inner material in such a way that this incidence angle is greater than the critical angle. So you have total internal reflection of every bounce. So that kind of by definition is a waveguide. Yeah. And this is one way of analyzing a waveguide. It's not the only way. So it's one way of conceptualizing what's going on. Okay. So what if you had the situation, and obviously for total internal reflection, N2 has to be bigger than N1. What if you had the situation where you need to confine light to a region that has a refractive index lower than what's outside of it? Well, you can't with this because you can't get total internal reflection. So instead, what you can do is build a multi-layer stack here and build a multi-layer stack here so that when you reflect, the multiple reflections from all the interfaces add up coherently so that you have very high reflectance at the interface. You have constructive interference. So now you get high reflectance because of the Bragg mirror properties of the stack instead of high reflectance because of total internal reflection.
So when we analyzed dielectric slabs, I think it was dielectric slabs, we determined that there's no way to get 100% reflection, but there was 100% transmission. How does that, is that still the case with this, I guess? Is what I'm
So
saying?
you'll always have some loss.
A little bit of leakage, but you can get really small.
You get pretty small, yeah. But you'll never get it, I mean, you'll never get the loss to be as
Yeah,
low as
that
you
is
get here.
inside of it.
Here, I mean, you can get it down to just material loss. Here you'll have material loss plus loss from the Bragg mirror. But in the case where you need this refractive index to be lower than anything you have available around it, this is the only game in town. And so you have to go there. And it's an awesome way to go if you can build it. And the beauty of what Dr. Hawkins has done is they can build it. So
So what would be the case in which you would need that?
oh, so this is water. Refractive index 1.33. You know, there's nothing you can put around water. It's going to have a low refractive index, so you get CIR. And as soon as you have water, now you can do all kinds of biological applications because you have aqueous solutions of biomolecules confined in a waveguide, which means that when you send light down that waveguide, it's going to interact with whatever's in the water. And so it's a really nice platform. Yeah, or the slow light stuff. Instead of water, you've got a gas of rubidium ions. And so this gives a long interaction path. So, I mean, once you have this structure and its capabilities, then anything low index you want to stick in there is fair game.
Okay. This is for analysis purposes, essentially.
Yeah, basically. Yeah, I mean, slow light, then that's more for atomic clock types of applications.
We put this on the air core fibers for like laser stacks because I think the power inside the core is like too high for the higher index materials.
Yeah, that's a possible thing too. Yeah, I mean, if you're trying to transmit power from one location to another, then often you'll use a fiber. And rather than using a solid core fiber, you can use a hollow core fiber that's a photonic band gap fiber. And so that's a nice way to go.
Is that the same thing as this, or is that different?
So this is waveguide on a substrate. And then the photonic band gap fiber is fiber.
I guess I'm not understanding what the difference is in fiber, just substrate tube.
I mean, you don't have a substrate that you're putting stacks of things on.
Sure.
And so with the fiber, I mean, it's easy to make it long, to snake it around things. This, where you're just doing something that's substrate. Now, I mean, it's the difference between kind of copper wire and an integrated circuit. I mean, integrated circuit, you've got to do it on a substrate. Copper wire, yeah, it can be just hanging in the air. So, similar sort of difference between the two. Mhm. Yeah. Yeah, so if you go through Dr. Hawkins' catalog of papers, you find all kinds of really interesting uses for this. You know, it's good stuff. Okay, any other questions? All right. Okay, so excited to dig into a paper and learn the method? Yes. No. All right, well, it'll be good practice for you because through your careers, often there's stuff that's only available in papers, and so you've got to learn it out of the papers. So it's good to have some practice doing that. The funny thing, though, is all papers are not created equal, and meaning some papers can be pretty dense and difficult to get anything useful out of. Whereas other papers can be really clear and pretty straightforward to get useful information out of. And it turns out the paper that I'm giving you is one of the latter. It's a really exceptionally well-written paper. So it's a good one. Okay. So that concludes our multiple reflection, or rather our multiple beam interference section. And now we get to move on to the last section of the course. Now, you'll notice, or you may remember, that we missed a class way back when I had to travel.
Mm-hmm.
And we said we were going to figure out another time we could meet. Well, turns out we don't have to do that. We've gotten far enough along that we don't really need to make up the time. So unless you have a burning desire to throw in another class period for no purpose, I mean, I'm sure we can find a purpose, but we'll just call it good and finish up with the material review for the next couple of lectures. Okay, so the last section then is on absorption and dispersion. And this is exceptionally useful, practical stuff. I've used it a lot throughout my career. And we're going to take it in different pieces. The first thing is we want to look at absorption in dielectric materials. But wait a minute, when we defined dielectric materials, we said there was no absorption. So here, what we want to do is relax that assumption and say that our dielectric material is still pretty much a dielectric material, but it's got some absorption to it. And so what happens in that case? And if we go out and just make some measurements, what we find is that if we have some interface between some material that's the incident material, and then this is the material of interest here. If we've got light incident, then the light that gets into the material and propagates, as it propagates, because of the absorption, the amount of light will clearly decrease. And also you can see that there is an issue of, well, how much light that's incident actually makes it in. So same thing as saying how much is reflected. So we're going to save this question, answer it a little later. we're going to start with assuming we're just going to look at the light that makes it through the interface. And so right here, just barely into the material, just infinitesimally into the material, we'll say that we have an irradiance, I, and call that the origin. So this is, say, the z-axis, just to give it a name. So this is I at z equals 0. And then if we make a bunch of measurements, what we find is that the irradiance at a depth z into the material is equal to the irradiance that started out times an exponential decay. And we can write the exponential decay as e to the minus alpha z. And so alpha, we call this the absorption coefficient. And typically, it's measured in units of inverse centimeters. Not always, but it's pretty typical. Okay. So that's what measurement tells us, is we get this exponential decay.
Are you going to Beer's law? Are you going to Beer's law?
Yeah, that is Beer's law. Yeah. Yeah, so this has a name, and it's called Beer's law. I mean, we could look at it from a differential equation point of view, but yeah, let's just cut to the chase. So that's the basic result. So for measurement, we see that that's true. Now, when we talked about dielectric materials, we never said anything about absorption coefficient because we said there was no absorption. Instead, what we did was we found that everything about a dielectric material was described by the permittivity. So the refractive index came out of the permittivity. Because we could write the permittivity as permittivity of free space times the quantity 1 plus the electric susceptibility of the material. And that's equal to the relative permittivity times the permittivity of free space. So relative permittivity is just 1 plus the electric susceptibility. Okay, fine. So now, though, we have this absorption, an absorption coefficient. And yet, when there is no absorption, everything is described by the dielectric constant or the electric permittivity. So it'd be useful if we could generalize here to take into account absorption in the framework of this permittivity that we've already talked about. And it turns out that we can do that if we let the susceptibility be a complex quantity rather than a real quantity. So we can say then that the electric susceptibility has a real part and has an imaginary part. So single prime is a real part, double prime is the imaginary part. Okay, then in that case, when we look at the dielectric constant, it's still going to be equal to 1 plus the electric susceptibility, but now the electric susceptibility is complex. So we can write that as 1 plus the real part of the electric susceptibility plus J times the imaginary part of the electric susceptibility. And therefore, the dielectric constant is going to be complex. It's going to have a real part, and it will have an imaginary part. And the real part, clearly, is just 1 plus the real part of the electric susceptibility, and the imaginary part is just equal to the imaginary part of the electric susceptibility. So if we define things in that way, notice that if we have no absorption, then the complex part of the electric susceptibility goes away, and we're just left with the real part, and therefore the dielectric constant is just what it was before, and the imaginary part of the dielectric constant goes away. So the question is, well, gee, how does that absorption coefficient connect with the imaginary part of the dielectric constant or electric susceptibility? So that's where we ultimately want to get to, and it'll take a little bit to get there. But let's get started towards that. Okay, so remember that the components of the electric field, the components of the magnetic field, the components are solutions of the scalar Helmholtz equation. So I said the components, meaning the x component is a solution of the scalar Helmholtz equation, the y component, z component, etc. And so we can write the scalar Helmholtz equation as the Laplacian of some scalar quantity, just call it b for the moment, times k squared. B is equal to 0. And k squared was our wave number. And so k, we saw, was equal to omega, the angular frequency of the electromagnetic wave, times the square root of the permittivity times the permittivity of free space, or permeability of free space. And so the permittivity we can write as permittivity of free space and pull out the dielectric constant as a square root in its own square root over there. So it's the same expression. We've just substituted in for the permittivity. And then we look at this here, and we say, oh, that's just 1 over the speed of light in free space. So we can write this as omega over speed of light in free space times the square root of the dielectric constant, and the dielectric constant is 1 plus the electric susceptibility. Okay, fine, but we have this situation where the electric susceptibility is now complex, and omega over c is just k naught, wave number in free space, and this electric susceptibility is complex. So we've got the square root of 1 plus this complex quantity. Okay, now before, what did we call that? Yeah, N, the refractive index. So this is just the refractive index. So if we continue to call it the refractive index, notice it's the square root of a complex number, therefore it is also complex. So we can write the refractive index as having a real part, n prime, and then I'm going to do minus j n double prime instead of plus j n double prime. Just because things work out nicer that way. And it'll lead to not having to carry around an extra minus sign later. And so evidently this is equal to the square root of 1 plus the real part of the electric susceptibility plus j times the complex part of the electric susceptibility. Okay. So basically, if we have a complex electric susceptibility, that leads us to a complex refractive index. So we're good with that? Okay. And then with this complex refractive index, we still are solving, this is still a solution of the scalar Helmholtz equation, which is what each of the components of these fields has to be a solution of. Okay. Oh, and just for fun, in some of the optics literature, this called N. And this is called K. Not the wave number. Yeah.
It's terrible.
Out of all the letters you could choose.
I know, isn't that awful? But just be aware that in some of the literature, when you are given the values of the complex refractive index, you'll be given them as N and K. The real part and the imaginary part of the
And
refractive index.
They still refer to the wave number as K as well?
Generally, no. Yeah. But just be aware it's out there. Don't be confused. I mean, I'll just use this notation.
Excuse me, what implementation for the reactive index you have minus before complex before?
Here, why is the minus sign there? It will make it so I don't have to carry around a minus sign later.
Okay.
So it's just convenience is all. Okay, so, if you have the electric susceptibility and you want to get to the real and imaginary parts of the complex refractive index, I mean, it's just algebra. You can do it. So n prime is equal to a cosine of a parameter, we'll call it phi, divided by 2. And then n double prime will be a cosine, or rather sine, of phi divided by 2. And a is equal to the square root of 1 plus chi prime, quantity squared, plus chi double prime squared. And then phi is equal to the arctangent of chi double prime over 1 plus chi prime. So it's not that hard to do. On the other hand, if we're given the real and imaginary parts of the refractive index, we can always calculate the dielectric constant, and the dielectric constant is still the square of the refractive index. And so that's going to be n prime squared minus n double prime squared, and then minus j to n prime n double prime. So clearly, the real part of the dielectric constant is n prime squared minus n double prime squared, and the imaginary part is equal to minus 2 n prime n double prime. Okay, so it's easy enough to go between complex refractive index and dielectric constant. So we can go either way. All right. So now we need to connect back to this absorption coefficient that we get experimentally. Let's see how it connects back into this complex refractive index, which connects back into the dielectric constant. So let's say that that we have an electromagnetic plane wave, and let's say that it's propagating in the z direction, and let's say that it's linearly polarized in the x hat direction. Then we can write down the complex amplitude vector of the plane wave, and what will it be?
So like.
X hat, because that's the polarization state, yeah.
Amplitude E naught.
Amplitude, okay, and let me just give it a symbol A.
You're saying monochromatic.
Well, it's a plane wave.
Sure.
Yeah. Yeah, that's good.
E to the J.
E to the minus j c hat.
E to the minus j k z. and you're wanting to stick an e to the j phi in here, and you're absolutely right to do so. Let's just say this is complex.
Okay.
So it has our amplitude and our phase in it. Okay, fine. That looks good. So notice then, x hat a, and then here e to the minus j k. Notice that k is k naught times the refractive index times z. Right? Okay, so we can substitute in for refractive index, so we have a e to the minus j. And then we've got a, I guess we'll just write it in here, k naught n prime minus j n double prime times z. And so we can pull out the n prime term, so let's call that a e to the minus j k naught n prime z. And then the n double prime term, notice we have j times j, which is minus 1.
So it goes
Or,
positive.
and we have minus times minus, which is 1, so it leaves us with a minus 1. So we have minus k naught n double prime z. And that's why we had a minus sign here. Because we look at this, and this piece right here, what does it look like?
That's your
No,
That's just your phase.
yeah, that's just a normal propagation through the material.
Yeah, normal plane wave.
Yeah.
should that have a J?
Here?
Yeah.
No, it should not. Minus j times minus j
Oh.
is minus 1. So what does that look like?
Absorption coefficient.
Exponential decay.
Yeah. Negative K-N double.
Yeah, okay. So the irradiance as a function of z is proportional to the magnitude squared of E, right?
Yes.
Okay. So, and that's going to be magnitude squared of A times e to the minus 2 k naught n double prime z.
Yes.
And I of 0 is proportional to a squared. Right? So doesn't this look like I of z equal to I of 0 e to the minus 2 k naught n double prime z?
Yes.
Which, looking at this, says, oh, okay, so that means the absorption coefficient, alpha, is just 2 k naught n double prime. Aha. So, the imaginary part of the refractive index, where did it go? There it is where the absorption is at. And we can easily calculate the absorption coefficient. It's no big deal. So, by allowing ourselves to use a complex refractive index, we take into account absorption. Because the imaginary part of the complex index is all about the absorption. And when the imaginary part is 0, we have no absorption. Okay. So that makes it really easy to account for absorption. It's just the complex part of the refractive index, which comes from the complex part of the permittivity. Okay.
That again comes from the complex part of the electrical susceptibility, right?
Mm-hmm. Yes, exactly. Yep. Okay. So this is a critical relationship. So,
Excuse me.
Yeah.
If we have n that is complex, then Snell's law and those stuff still
Is what?
working. Snell's law and
Snell's law?
Yeah.
We're going to get to that next time.
Okay.
We'll see exactly how that works, which is, I know, the case that applies to the model you're building. Yeah. Okay. Well, at this point, we're ready to do an example. We've got 1 minute. You want to do an example in 1 minute, or shall we just save it for next time?
Save it.
Okay. I heard save it for next time first, so we'll do that.